So within physics, the branch of mechanics can be broken up into two parts. So the first of those is called kinematics. That's the study of an object's motion. The second is called dynamics, which is the study of how forces act on an object to change its motion. And part of what we're trying to emphasize in that definition of dynamics is that the change in motion is really the fundamental idea here. So historically, we tended to wrestle with the question, what keeps things moving? And this makes perfect sense because put anything into motion and at some point it's going to come back to rest. So this led us to think that the key question was, well, what keeps things moving? When in fact, this is really the wrong question. The right question to ask is, what causes an object's motion to change? And so this is where how, through Galileo on into Newton, realizing that we were asking the wrong question became so important. So part of Newton's genius and why we pay so much attention to him in terms of studying dynamics is because he was the one to really recognize that we were asking the wrong question. Now, the nice thing is that there's a relatively straightforward and simple answer to this question. Balanced forces act to keep an object's motion constant, and unbalanced forces are needed to change an object's motion. So when your forces balance out, the object's motion will be constant. When your forces don't balance out, your object's motion is going to change. And this is encapsulated best in Newton's first law. So if you ask students within the class, what's Newton's first law? Almost everyone's going to say objects at rest remain at rest and objects in motion remain in motion unless they're acted on by a force. And as we'll see with several of Newton's laws, they're critical details that we often neglect in sort of our most common way of expressing it. So it just so happens that objects at rest remain at rest. That part's okay. And objects in motion continue to move in a very special way. They continue to move in a straight line at a constant speed unless they're acted on by a force. So what this does is it helps us define some new ideas. One of these is it describes what uniform linear motion is. So that's motion with a constant velocity, and you have two options for uniform linear motion. You can either remain at rest, meaning your velocity is zero, but it stays zero, or you can move in a straight line at a constant speed. So again, that also has a constant velocity because your speed isn't changing, right? That's the magnitude of your velocity. And you're also moving in a straight line, so your direction isn't changing. So the velocity vector remains constant. The second idea is inertia. And again, this is an object's tendency to resist changes to its state of motion. So part of what Newton's first law is describing is that the issue is not what keeps an object moving. Effectively, if you leave an object alone, inertia is going to keep it moving. So inertia is basically just describing the principle that says if you leave objects alone, they will continue to do what they were doing before in terms of their motion. Last new concept, and again, it's not new, we've been working with it for a while now, but this gives us sort of a new definition for force. And it's a force, in some sense, Newton is defining a force to be what you have to exert on an object to change its motion. So if you just leave an object alone, its motion won't change. You have to exert a force on an object to get its motion to change. So here's just a block, right? And again, if I let it go, there'll be a gravitational force that acts on the block and pulls it downward. Meaning that presence of a force, under that presence of a force, the block's motion is going to change, right? So there's an unbalanced force here. And so that block won't stay where it is, and in fact it will fall and it will speed up as it falls. So its motion will change and it will continue to change as it falls. All right, so again, there's one more detail to sort of come back and add here. Objects at rest remain at rest, and objects in motion continue to move in a straight line at a constant speed unless they are acted on by a net force. And so what does this net force matter? Why has that become important? Well, mostly what this is getting at is the idea we talked about on the very first slide in terms of balanced forces versus unbalanced forces. So when we talk about balanced forces, what that means is all your forces, when you add them up as vectors, they cancel out. So there's no net force, which means that your system is in equilibrium. So you can still have forces that act on your object, but if they cancel out when you add them up as vectors, then you have no net force acting on the object, and therefore your system's in equilibrium. If there's no net force, there's no acceleration, and your velocity is constant. So without a net force being present, you don't change your object's motion. On the other hand, if you have an unbalanced net force, so again, the net force just says add up all the forces as vectors, and if you don't get zero, then you have what's known as an unbalanced net force. That unbalanced net force will change your object's motion by causing acceleration. So again, we can think about our same block, only this time, instead of letting it go and watching it fall, if I simply have the block sitting on some table or sitting on some surface, well, there's going to be a second force that's present. In this case, it's a normal that's going to hold the block in place. So the net force, when I add up, in this case, the normal and the weight, those two things cancel each other out. They balance. I have zero net force. My object's motion doesn't change. Again, it's at rest, and it continues to stay at rest. But I can take that same block, and I can push on it. But notice if I push on it so that the block starts moving to the right, but my applied force is the same as the force of kinetic friction. So I'm pushing on the block to the right, but there's this additional force of kinetic friction that's pushing back to the left, opposing the motion of the block. If the applied force I exert and the friction force the surface exerts, if both of those exerted on the block again are equal, I still have a zero net force. The object's motion doesn't change. It's moving in a straight line at a constant speed, and it'll continue to move at that constant speed. If, on the other hand, I push harder, so now my applied force is greater than the force of friction. Those two forces don't balance out anymore. They don't cancel when you add them up. And what you have is you have a non-zero net force, which means that I'm going to end up changing the object's motion. As I push the block to the right, it will move faster and faster and faster as I continue to push it with this force that's greater than the force of friction.